Hi, everyone. I hope we are having a great evening. So, my name is Taiwo Gabriel Momule, and I'm here to teach the machine learning course for this semester. Um, I'll be introducing some of the um, information that is required for us to know before starting with the main course content. So, as you can see on the screen, the course information includes our weekly lectures from 10 to 12 p.m. on Mondays. And I'm also available for office hours between 3 to 4 p.m. And if you have any question or discussion with me, you may also contact me via the course link. This is my information. As I said earlier, my name is Taiwo, and these are my research interests. I conduct research in the broad field of data science and machine learning, precisely to address statistical challenges and methodological problems in machine learning. I'm also interested in applied machine learning research, where we applied various algorithms to solve complex problems in spatial analytics, public health, and epidemiology. So moving forward, um, so this is the aim of the course. I'll be introducing you guys to the concept, theories, algorithms, and tools of machine learning, as well as the applications in various domains. We'll discuss a number of machine learning algorithms and try to implement them using Python programming or R, whichever is actually more convenient for you. My instructions will be simple and basic, so you can really understand the core concept of what machine learning is all about. Our lecture will, of course, I always prefer an interactive session with my student, and I'll be very happy if we could, interact, be open to discussion, tell me what you feel you don't understand, and I will definitely explain using different examples, different scenarios, concepts that you're more familiar with. And we'll also try to go through some practical sessions in class and, sometimes take home assignments. So you can have a feel of the concept and also how to implement them in a real life situation through programming. I would like to encourage you guys to try as much as possible to be available for every lecture. This is really necessary. Um, while I understand that situations, unforeseen circumstances could happen, um, I would really appreciate it if you guys could, be available for every lecture and try to attend as much as possible. Moving forward, we have some resources that can really help you to learn more about machine learning, because reading tends to improve your idea and your knowledge about this course. While I would try as much as possible to explain in detail so you can really understand the concept of machine learning, grasp the implementation tools and techniques that are used, and other aspects that may be relevant to you. I would also advise that we should try as much as possible to improve our learning through going through by reading this text that are displayed on the screen at this time. At the end of this course, I expect you, I want you, and I would love if you could put in the work. So the learning outcomes includes understanding the key concept of machine learning methods, the machine learning pipeline, generalization in machine learning, as well as a detailed understanding of a number of machine learning algorithms, including their implementations in Python or R programming. So I have always been optimistic about my student, and I would appreciate it if you can try as much as possible. If you feel you are not in line with the lecture, or there are areas that you do not understand, you can reach out to me via the course link, or you can come to my office during my office hours to reach out and ask your questions, what you need to know, where you feel you need more assistance and help. I'm always available to help my student. So please come around. So there are three modules. This lecture is divided into three modules. The first module is introduction to machine learning. The second module is generalization and learning methods, while the third module involves the discussion of several machine learning algorithms, including the regression algorithms and the classification algorithms. So, however, we may not be able to complete all of these discussions in a single lecture. So for this lecture, we'll try as much as possible to complete the first module, then move on to the second module. And so we begin. What is learning? We have all been, hearing machine learning. Machine learning, it is not a new concept, and it's a robust, topic. But precisely what do we mean by learning? When do you say you learn? So before I will explain this, I want you to picture yourself, entering an environment that is new to you. For instance, a first year student that just, that recently got admitted to study a program in a university. The student has a lot to learn. No, it has a lot to learn concerning the course itself. So concerning the program, taking several courses, learning the academic environment, building relationships with co-students, even building relationship with faculty. There are a lot of, processes involved when learning a new thing entirely. So in the first instance, the student may struggle to really understand everything that is going on within its environment. But over time, no, the student tends to improve. It's just like you're comparing the experience of a first year student and a third or fourth year student. You can easily see or delineate the difference between the first year and third year student in terms of experience about a particular program, if they are both enrolled in the same program, or about the academic environment or every other, every other thing that is within that environment. So look at it from the angle of learning. We see learning as a process by which a system, the system in this case, let's say a student, improves performance from experience. As the student tends to move from the first year to the second year to the third year, the experience tends to move, to improve. So we say a computer program is set to learn, according to Tom Mitchell. He defines learning formally as by saying a computer program set to learn from experience with respect to one class of task and performance measure if its performance at task T as measured by P improves with experience. So here, the student goes through several courses, takes a lot of assignments and tests and all that. So as the student reads different content, takes some lectures, engage in different assignments, the student performance tends to improve over time. And we measure the performance by, examining the student on a set of test questions. And then we mark, we grade. So this is just the scenario. A computer program improves with experience when the program is giving an exam or a test, in this case, a task T, and then we grade the performance of the computer program with respect to some measures, let's say, for instance, accuracy. And then if the performance improves with time, we say the computer program is said to have learned efficiently. Learning is essential for an unknown environment. Apparently, when you enter, a new environment that is unknown to you, the first and the most basic thing that you have to do is to learn what the environment is. There are a lot of variables that that make up the environment. So learning in this instance is really crucial for you because you do not at that present moment have a detailed knowledge of what the environment is all about, or the components or the variables that are available in that environment. So you need to learn. Um sorry. So we continue. What do we talk about when we talk about learning? Learning general models from a data of particular examples. Okay. From the context of machine learning, we want to learn what are the things at the basic level. I would like to explain it this way so you can understand. We want to learn at the basic level abstraction. What are the things that are available in a data? What are the patterns? What can we get? What are the relationships among the variables? How does the sample, what is the distribution of the samples? What is the distribution of the variables in the data? How does this how do the variables relate with one another? There are a lot of questions, there are a lot of things to learn from a data. At this point in time, we do not know what to learn. We do not have precise information about the data or about the things, the information that are available in the data. So the only thing we can do is to learn from the data through modeling. We develop a model that can learn some information from the data. Data is cheap and abundant. The pervasive increase in data generation currently is is extreme and is large. We are generating data from different sources. We have the internet. We have computing devices. We have different domains, different applications. We keep generating data every day. So there are hundreds of or thousands or millions of data that are generated every day. So since these data are available, they are not really expensive to generate. It is very good to develop a model that is a good and useful approximation of the data. Why do we learn? Of course, we want to learn. We have the data. Data is cheap to generate. We are interested in so many things concerning data. But why do we learn? Why do we have to learn? There are specific scenarios. Traditionally, there are, practitioners have, been using, data practitioners have been using conventional approaches like statistical methods to, analyze data over the years. But in the present era of big data, these statistical models, they may not be sufficient to generate relevant insights and also to learn the intricacies and the complexities in big data. When I say learning the intricacies, I mean to learn them efficiently and within time and scope with less resources. So here, statistical models may actually experience difficulty in learning appropriately from big data. That is why we need an intelligent model that can extrapolate rules, that can learn from the data and generate a model that can provide relevant insight or information from the data. So we now talk about machine learning. The broad field itself is artificial intelligence that consists of several subfields like computer vision, like natural language processing, like expert systems. Machine learning is one of them. So machine learning is a subfield of AI that gives us the potential to develop a learning algorithm, an intelligent model, to search through an n-dimensional space of a given data in order to find acceptable generalizations from the data. We have our data sets. We need a model that can learn the relationship that exists between a set of features and a set of features, we call them independent variables, and a dependent variable, which is the target feature in the data, and generate acceptable relationships among them. So, for instance, you have a data set that consists of several input variables and another variable. So what we are interested in is, due to this extreme the size of the data, we want a model that can learn efficiently the relationship that exists among the variables in the data or between the input variables and the target class in the data. The essence of doing this is to create a model of that relationship so that when we have a similar data that is generated from similar distribution, we do not necessarily have to build a new system or a new model. All we have to do is to feed in our trained data, the new data that we have collected. Now our model will be able to give us the insight to generate patterns, extract meaningful insights from the data, and tell us what is going on. From that sense, generalization means that the knowledge and experience learned by a machine learning model from historical data, samples in the data, are used to estimate future predictions on same samples. So we from this context, we have we believe our model to be exposed to a set of data where the model can learn relevant information, gain the knowledge from the data, learn the relationship that exists among the variables, save this knowledge within itself, then use that knowledge to estimate or to generate predictions from new data that is obtained from the same data distribution. And how is machine learning different from traditional programming? Imagine in the last 10 to 20 or 25 years ago, where we are more focused on software development. We develop a software, the software is installed on the system. We feed in our data into the software and we get our output. For instance, a web page, for instance, a website where the website is a web-based software. You enter your details and you get the output. In that instance, when the needs or the business needs change, or most times what we do is to create a new software for the updated business needs, or probably update the software into another form or shape so as to meet the current or future demands of the business. There are limitations to this. Data could change, needs could change, also the cost involved, the expertise involved, the time and the scope requirement of the software. There are lot of processes involved to achieve that goal. But in machine learning, we are not interested in creating a software. What we want is we want to create a model of our data. The model also is software. Actually, we always can say it's software, but it is what we are more. It is not really a software until it is produced. So we want to create a model of the data. And in order to do that, the model needs two inputs, the data and the output. So when the data knows the expected output, and the data, when the model knows the expected output and the data is fed in, the model tends to create a mapping relationship between the data, which is we call in this instance the data are the input variables. We'll get to that point, and then the target class, which is the output. So when the business needs change, that is where machine learning is, is different from traditional programming. When the business needs change, and you have the data of the same distribution, you do not necessarily have to create a new software like in traditional programming. All you have to do is to feed in the new data to the already trained model, as long as the data is coming from similar data distribution as the one that was used to train the model. Precisely, in machine learning, we focus on, just like what I recently discussed, we focus on acquiring a model from data, modeling a data. And in order to do that, the model involves, needs a number of components. For instance, what we learn from data, we learn the parameters of the model based on the data. We learn the structure of the model based on the data. And we also learn the specific task that we need to solve based on data. Apart from this, learning from the data, we believe there are two, we just have to talk about the roles of statistics and the science. Mind you, I would like to point our attention to one information. Machine learning is not replacing statistics. Machine learning is complementing statistics. Statistics is really important in machine learning. There are several fields that are, that are necessary or that are required to succeed in the process of machine learning. Statistics is one of it. Computer science, mathematics, even the business experience. Then some ask probability is also required, which is also an aspect of statistics. So what are the basic terminologies that we need to understand before, venturing into that broad concept, machine learning? There's so many concepts involved, but we need to understand some of the, basic terminologies that are required in this field. One will say a model. What's a model? Basically, I could say model is an abstract representation of an entity. So it is not the real representation. But when you learn from data, we believe that we have a kind of representation of what we have learned from the data. So a model is a specific representation learned from data by applying some machine learning algorithms. A model is called a hypothesis. You have an algorithm, the algorithm, the data is fed into the algorithm tries to learn the relationship that exists among the features in the data. They create a model of the data. That is a basic explanation of a model. What is a feature? A feature is an individual measurable property of our data. You have, for instance, you can view an Excel sheet in front of you. You have columns and rows of the data. The rows are called samples. You can call them observations, or you call them instances or examples. We can see when you read literature, papers, machine learning papers to be precise, you can see different, terminologies used to represent samples of the data. So samples include instances, observations, or examples. A feature can be, these are the columns in your data, but then there are several terminologies that can be used as well. You can call it a feature, you can call it covariate, you can call it attributes. These are the terminologies that are related to samples and features in the data. So you as a student, you have some properties or characteristics that can be used to describe you. For instance, your age, your gender, your address, your weight, your height. These are measurable properties that are specific to you. So each of these is called a feature. Then we have target label. A target label is the value to be predicted by our model. I would like to go to a slide so I can really explain better. Okay, let us continue. When we get to that slide, I will point our attention to that. We have input features. For instance, I'll say age, gender male, gender, that's a female, weight, height, and all that. Then we have one of the columns that says girls' school. Then we have another values for all of those features. Then the same column says boys' school. So this representation where we have several input feature and a feature that is called target, which represents the type of school for each student, that target column, we call it the label, that data. Training is just an idea where, our model is exposed to learning. If set of features, input features are given to the model, so the model can learn to extrapolate rules to learn the relationship among these input features and the label, create an hypothesis of the data, then create a mapping relationship among the input features. It's just the learning phase. Just like a student, when you get to school, you have to learn. Then prediction. Once a model is trained or has learned the relationship among the features, create a mapping relationship, knows what is going on in the data, The train model is, tested, giving a new data that it has not really experienced before to give a specific prediction. Moving forward, so here I will give a detailed breakdown of the machine learning framework. All the information we have been discussing here, this comment slide actually summarizes the flow of learning and testing or prediction of a machine learning model. So for training, you have, assuming you have, I will give a scenario here. Remember our student scenario. The student has been admitted to study a program on, on campus. At, the initial stage, the student does not really know much about the course. So the student attends lectures, goes to the library to read, engage in personal self-development, personal reading. The student reads, blogs, articles, papers on, that specific course. So as the student tends to learn by attending lectures, by doing personal readings, by engaging in group discussions, taking assignments, the student is acquiring knowledge. The student is, training. The assignments, the class lectures, the textbooks that are available in the library, blogs, articles, papers that are available to learn that course, all of these combined together are what we call our training data. So this data, combine together your class lectures, assignments, and all that, they are what the student is given to learn that course, that specific course program. The student in this instance is just an algorithm that does not really know much about that course. So the student has to learn what is going on in that course to understand, just like you're learning machine learning here. You do not really know in detail what machine learning is all about. So you need to learn, go through different class lectures, take assignments, go to the library to do some self-reading, read some journals online, read some articles, some blogs on machine learning and all that. So as you do that, you are learning, you're training. While you do that, what the student has done after going through the whole process of learning, the student becomes a trained student. So in this instance, a learned model from this framework. The student has learned, he has been trained, he has read, he has captured the basic understanding of that course, and now the student is now self-sufficient with respect to the knowledge, the information available in that course. Now you will realize that after you have gone through all of your class lectures, assignments, and all that, it's now time for exam. I will have to create a scenario here so you can understand. You will realize that the time it takes to write an exam is shorter compared to the period or the amount of time it takes to, attend your lectures, do assignments, So in a whole semester, you have 4 months. You can go through lectures, assignment, and other for like 3 months. Then you only write your exam within, let's say, a week. For a particular course, you write it for a day, 2 hours. So you will realize that it is practically impossible for the course advisor or the course lecturer to set questions, exam questions, that are not related to what has been taught in class. So in this instance, we believe that the training data, which consists of your lectures, assignments, and all that, and the test data, which is your exam, must come from the same distribution, the same knowledge, the same concept. As I'm teaching machine learning, as a course, I can't set in exam. I can't set questions on natural language processing. I can't set questions on large language models. I can't set questions on cybersecurity. Because what I have taught in class, what you have been trained on, is the concept of machine learning. Now you go to the exam hall, you met questions on cybersecurity. They do not align. The exam questions, which is the test data, is coming from another distribution, another data distribution that is quite different from the training data. So it is very essential that both the training data and the test data must follow the same or similar data distribution. So the student here is examined, is tested on, is given an exam questions with the test data, then the student writes the exam. The student now is a trained modeler in this instance. The student writes the exam. When the student finishes the exam, at that point in time, the student is going through what we call testing phase. So when the student finishes the exam, then the exam question is marked and graded in line with the marking scheme. So the course lecturer who sets the question has a predefined marking scheme. The marking scheme in this instance is the label of the data. So when the student is evaluated on the test data, the prediction or what the student has written in the test paper, which is what we call model prediction, they are matched together. The model prediction is matched with the label, the data. The student answers are matched with what is available in the marking scheme. So, and the student is graded according to what he has written. The model is evaluated according to how well the model predicted the label of the data. If the label are categorical values, yes or no, for instance, zeros or one, for instance, the model is predicting probabilities that this sample is in this class, this other sample is in the other class. That is for classification problem. We'll get to that point. When we get there, I will explain better. It's an interesting course. So we can move forward. So this is just a machine learning framework explained in line with student learning experience. Then the framework is further explained formally. Here, sorry, there are some issues with the slides here. I think it was when I was typing it, but I will explain. And if you have any questions, please do not hesitate to ask me. This is just the basic form of machine learning framework. Here, we have our model, which is the student. The student that are the trained student here. So here, the student is given a set of questions to answer. Then the student tends to answer this question based on some personal characteristics. This W here represents a set of parameters that are available for this model. So the F model, the function here is our trained student. This W represents the personal ability, characteristics of the student, what the student has learned, how well can the student apply what he has learned on the questions given. So for a student to answer, let's say, a specific question in the exam, let's say a student is given a question, discuss what let me try to frame a question. What is machine learning, for instance? For such a student to effectively answer that question, the student in this system haven't gone through different class lectures, different assignments, different papers, journals, and all that, will answer that question here based on the knowledge acquired and based on other personal abilities. The ability to remember what he has learned, the ability to now write what he has learned, the ability to write it efficiently. So a model tends to predict from a particular data based on the model parameters. These parameters could be intrinsic and it could be controllable. They may be personal to the model, and there are some that are not personal, that can be tuned or controlled. For instance, in the case of our student here, we can't control the ability of the student to learn. But what we can control is our ability to allow the student to be exposed to several learning resources, and our ability to explain the concept in a clear, personalized manner, using the kind of personalized learning approach. That is a learning approach that takes care of the personal needs of the student. So as you can see the explanation here, we have a set of label examples where our X, we have a set of example X1, Y1, X1 is the data, Y1 is the label to Xn, Yn. And then we are trying to generate, to produce a model of this data. So we apply the model to this. So we assume that this model has been trained. We apply the model on X, which is a test sample, and output a prediction Y. Our W here is a set of parameters that are available for this model. Moving forward, I would like to point our attention to two processes that are involved in machine learning. We call them inductive and deductive learning. In philosophy, these concepts are also being taught, where we try to learn from a very high level. We learn at high level. We learn in high level detail. Then we try to make specific conclusions based on the premises of what we have learned. This concept also applies to machine learning. We say at the heart of machine learning lies a symbiotic relationship. I usually call it a symbiotic relationship because both processes are involved. As we're performing inductive learning, we also perform deductive learning. So inductive learning occurs when the model learns the general principles from a training data. The student in this instance, at the point of training, going to classes, taking lectures, reading in the library, doing personal readings and all that, the student is going through what we call inductive learning. So the student is allowed to, work on, to learn several resources, several learning resources, and then capture the knowledge and experience needed to, solve complex questions about that course. Our model here is exposed to our limited available data, then to learn to learn the relationship among the features in order to create acceptable generalizations about the data. For deductive learning, once our model is trained, of course, I just as I've explained in the machine learning framework, the model is applied to a new data for prediction. So apparently, deductive learning allows our model to move from a general principle, learning all that is available about the data, the student learning everything about that course, going to classes and all that, to making specific conclusions. That is the student now answering exam questions and writing what he knows about that course. The interplay between inductive define the iterative nature of machine learning. So I'll come back to this statement when we get to the machine learning pipeline. Continuous learning, prediction, evaluation, adjustment process allow machine learning models to refine their understanding of the data and improve the performance over time. So again, when we get to that, to machine learning pipeline, I'll point our attention to this again. There's what we call decision boundary. This is actually applicable to classification problems. Let me just explain this in a basic form so you can really understand. You have a complex, a simple problem or a problem to solve. Assuming the problem is, classifying or predicting if it will rain or not in the morning. For you to for you to get an accurate prediction for the probability to rain or not, you need a set of variables. In this instance, predicting if it will rain or not is just, a binary problem, a binary classification problem. You want to classify a specific data to it will rain or it will not rain. And here you have several features. Cloudy weather, temperate weather. You have weather data sets that consists of different variables. So in order to do this, you need to compute to see the relationship that exists among these variables in terms of their values. Probably you come up with a simple, mathematical equation, sorry, that that you can estimate the probability of probability that it will rain or the probability that it will not rain. As you compute these probabilities, you realize that some values, assuming we represent our one of the classes as 1, the other class as 0, the probability that it will rain, if it is closer to 1, let's say that you got something around 0 0.6, 0 0.5, or 0 0.7, 0 0.8, that is a boundary for that class. That is, having a probability of 0 0.6 to 0 0.7 tends to be closer to 1. That means for that instance, for that sample, it's be rain. Then another sample is estimated based on your equation. The probability is less, is very small. Let's say 0 0.2, 0 0.1, 0 0.25. So this boundary for that sample, for that estimation, is closer to 0, the other class. So it may not rain. So as you do this for the different numbers of samples in the data, at the end of the day, you take an average of your probability. That can give you an idea of what may happen tomorrow. So we continue from there. As you can see here, this is an example. While we talk, sorry, before I move on to the next slide, while we talk about decision boundaries for classification problems, for regression problems, we talk about a regression line. That is, here you have two variables, for instance, x1 and x2. You have a line that goes this way, or this way, or this way. For a simple linear regression, for instance, that has two coefficients. So you talk about a regression line, or for a two-dimensional data, x1 and x2, or you talk about a regression hyperplane for n-dimensional data, where that is for a data that has more than two variables. Here you have just two variables, so you are open to 1, 2, 3, about 3 regression lines. But for a data set that has more than two variables, let's say x1, x2, x3, you are getting the regression hyperplane. When we get to regression, or in module 3, we will discuss that in detail. This is a simple illustration. This is an illustration of decision boundary. As you can see here, this is a simple rule that says that if income is greater than pi 1 and savings is greater than, as you can see here, this line, this line divides these two income, these two variables. It divides these two samples here. As you can see, here is a decision boundary that aligns, or that is equal to this equation. This equation actually generates this boundary. So in other words, we can say decision boundary is the outcome of the rule that guides that learning process. So here, that concludes our introduction to machine learning, and then we move to introduction to the first part of this lecture. Then we go to the machine learning pipeline, where we talk about the stages that are involved, from problem formulation to model development, model monitoring, and all that. All of the steps that are involved in developing a specific model in machine learning, and how the model is being, evaluated, trained, tuned, and all that. So we start with problem formulation, that is framing the right problem for the task involved. Of course, you always have a question in mind to solve before you can say you want to develop a model for this problem. You have a defined question that you want to solve. So we start with problem formulation, then from there we move to data collection and integration, data preparation and wrangling, data visualization and analysis, then feature engineering, model training and tuning, model evaluation, then communicating models results, model deployment, and lastly, monitoring models. What is problem formulation? Before the first thing in this pipeline is you asking the right questions. What is the question to ask to frame a problem for a data science project? This is arguably, sorry for that word, this is the most important part of a pipeline, also of a machine learning pipeline. Possible questions may include what is the current process being used? What do you want to predict? What are the inputs, data sources? What are the data requirements? What are the requirement analysis? So, you need to be clear about the question. For instance, you are given a problem. Let's say a company, gives you a problem. We want to know the current price variations, rental price variations in let's say Texas, for instance. What are the variation in rental prices of different um, apartments and buildings in, let's say, Texas? This question, they are interested in knowing the variation of the rental prices. So there are times the question may not be clear enough. It means the question may be vague. So you need to either break down the question to a very simple level, or if the question is not clear enough to you, ask your client, or ask the owner of the project to provide more information about their needs. So it is very important that you have a clear picture of what you're solving, what the question is all about. A clear definition of the problem at hand, the intended business value, and the metric for success will help in defining the initial hypothesis. Having clear definition of a problem, well defined, the business goal, the end goal, or the value, or the output of the project, or you have an idea what is expected, and you have the metric for success, the time frame involved, the scope of the project, and all that. This will help in defining the initial problem. Hence, understanding the problem's characteristics will provide insight into the type of data required and the selection of the right machine learning for modeling, as well as suitable performance measures. So before delving into data sourcing, data cleaning, data, exploratory analysis, model development, and all that, it is essential to, understand the problem in detail, have a clear picture of what the problem is all about. Then from there, we move on to, data collection and integration. Having understood the problem, characteristics, and the problem is well defined. The next question is to see if if there is enough and correct data to answer the three questions. At this stage, we need to obtain data. We identify the right data sources. How can we extract the data? When we extract data, how can we integrate them together? Sometimes the question, sometimes one data may not be sufficient to answer the question efficiently. So you may need 2, 3, or 4 data sets that needs to be combined to answer the question. And data could be sourced from an open database, for instance, the UCI Machine Learning Repository, for instance, Kaggle, for instance, DataWorld. There are a lot of open databases. It could be sourced from public databases. There is a difference between open data and publicly available data. Open data, you don't need access. You don't need to request for access, privileges before you access the data. You can use the data. But some publicly available data are actually, controlled by the government or some agencies or some organizations. So sometimes before you use them, it is always good to, secure either license or to request for accesses. So, sorry, access before you can use the data. Again, data could also be, provided by an organization, in this case, a third party. Sometimes you may not have access to, the right data, or the right data may not be available in an open database or a publicly available database, but data is owned by a third party organization. So in that instance, all you have to do is to contact them to request, access to the data. Again, you can also, scrape data from the internet. There are web scraping technologies using, for instance, in Python, you can use what we call Beautiful Soup or Selenium to scrape data from the internet from various sources. So framing the question will give you an insight into the right data, the right machine learning model, and as well as suitable performance measures required for the problem. After gathering data, integrating data, and all that, you need to clean the data and prepare the data for efficient exploratory analysis and for modeling. So this stage involves performing data cleaning and transformation. The result of a data science project largely depends on the quantity and quality of the data used for modeling. In fact, 70% of what we do in machine learning, they are spent on data collection, data preprocessing, and data preparation, because the output of a machine learning model largely depends on the quality and quantity of the data used to develop the model. Again, the output of the EDA stage, I mean the exploratory data analysis stage, to gather relevant insights, patterns, information, meaningful, actionable insight from the data, you need to obtain the right data for that problem. So well-prepared data for a model can improve its efficiency to generate improved accuracy during training and prediction. It is very important that the data is well prepared for EDA and modeling. Therefore, it makes sense to deliberate and review the available data so that they are processed and produce better and meaningful results. In fact, this stage, apart from modeling, or you're trying to obtain perform relevant exploration from the in the data, obtaining the right data can also tell you about the suitable pre-processing techniques to use. It is a lot, it contains several components that is required. And the output of this stage, has an effect on the result that will be obtained. Data preparation process could, include converting categorical data into numeric data, removing outliers, filling missing values or removing missing values, balancing classes, encoding labels, scaling data, different processes. When we get to the practical, the coding sections in our lecture, I will point every stage to you. So our coding structure will follow this pipeline. That is, as we prepare the data, the problem, we obtain the data, we prepare the data, we perform EDA. Every stage we align with our coding structure, so you can understand the pipeline efficiently. The fourth stage is data visualization and analysis. This is a part of data preparation where exploratory data analysis is performed. Why do we have to perform exploratory analysis? Actually, we do that to obtain initial assessment of our data. Initial investigation to discover patterns, spot anomalies, test hypotheses, and check assumptions with the help of some statistics and graphical representations. For instance, what is the mean? When talking about statistics, we can look at it from the angle of the descriptive statistics or the inferential aspect of things. Descriptive in the sense that what is the mean, or the distribution, or the median, or the mode. We look at different statistical measures to help discover patterns from the data. Again, we can look at if we want to do that to generate conclusions, probably perform a simple regression analysis. Then we can, with the help of graphical representations like plots, box plot, line plots, violin plots, scatter plots. These visualizations can give more information about what the data, consists, or what is going on in our data, to tell us, the sample distribution, the feature distribution, the relationship among the samples and the features, the relationship with the features and the data. We can perform, different. In fact, we can perform different tests, ANOVA tests, tests. We can perform correlation analysis to see the correlation among the features and the target, class. So a lot of activities can be performed under EDA. Precisely, the EDA involves summarization, aggregation, apart from what we have said earlier, and presenting the collected data for insight that may support or disprove the initial hypothesis. Remember, the initial hypothesis, that is the problem, has been framed in the first stage. So when we get our data and we clean the data, we need to perform this exploration before moving on to modeling. This tells us what we should expect. Probably when you get your model result, the model result can, the EDA result can give you more insight about your model result. So visualizing data helps to detect relationships between features or class imbalance or perform relevant exploratory analysis. Then again, we talk about feature engineering, which is the fifth stage in the pipeline. For feature engineering, we are interested in, there are times you can experience or you can have access to high dimensional data. When I say high dimensional data, I mean a data that has very large input features at probably a small number of samples. It may not be small and it may be small. But the most important thing here is that when we talk about the high dimensional data, we talk about the data that consists of large features. In a situation where the data consists of large features and very small number of samples, then we call that, in machine learning, we say this, we call that problem the cost of dimensionality problem. So for feature engineering, we are interested in, selecting relevant features from the data or extracting features. So we perform feature selection or feature extraction. And feature selection, there are several methods that could be used. Precisely, they are subdivided into the statistical based method, the embedded, the filter based method, and the embedded method. So, sorry, the filter based method, the wrapper based method, and the embedded based method. I would in our future class or in our next class, I would try as much as possible to explain these categories of feature selection approaches. The filter method, which is the statistical methods, the wrapper-based methods, which they are more of heuristics, and the embedded method, precisely learning models. So, and we also have a feature extraction where we try as much as possible to reduce the size of features by transforming the feature into another shape or another form. Possible approaches include what we call principal component analysis. We can perform singular value decomposition. There are several methods that are used on that feature extraction. So feature engineering involves augmenting. We can remove features, we can identify relevant features and select them, extract them, or add features. Several activities just to have a representative size or amount of features that can drive our model efficiently without the problem of overfitting or underfitting. We'll get to that point. If feature engineering is done correctly, it increases the predictive power of machine learning algorithms by creating features from raw data that help facilitate the machine learning process. So feature engineering is really key, especially when the data is a high dimensional data set. Sometimes after evaluating your model, prediction phase, we have to, don't forget that we have two phases in the machine learning framework. We have the training phase and we have the testing phase. The training phase is when the model is being trained on the training data or the developmental sets in order to capture the rules, to create mapping relationships among the features. And then the trained model is now, taken to the second stage, which is the testing phase, and tested on the validation set or evaluated on the training set, on the testing set to make predictions. So apparently, the testing set is a set that the model has not seen before. Remember, it was not used during training. So as we move on, sometimes when we test the model and we evaluate the performance, maybe the performance is below what is expected on average. It may be necessary to go back and re-engineer the features of the data to see if improved model performance and better result could be achieved. Moving forward, the 6 stages are model training and tuning. At the heart of machine learning process again is training the right machine learning model for the framed problem. We prepare what we usually do in this phase, at the training phase, is remember that our student here, which at the beginning when the student was admitted, is just a machine learning algorithm that needs to be trained. That is go through different class lectures, assignments, personal reading, and all that. So here we are splitting the data we have into 2 different sets, sometimes 3. Sometimes we can split into 3 sets, depending on the size of the data. So in a basic form, I will explain this and tell you what this approach is all about. So we have the data prepared. The prepared data, if there are different training approaches that are used in machine learning. We have the leave one out approach. We have the cross-validation approach. We have bagging. We have boosting, all that, which are just simple approaches actually. So, but here I will just explain the leave one out approach, which is being written here. The prepared data is split into a training set and a testing set. But depending on the size of the data, if the data is huge enough, it's large, sometimes we can split into 3 sets: a training set, a validation set, and testing set. So these 2 processes are done iteratively before we move on to the final stage testing set. The training set is fed into this selected machine learning model. In this instance, the student goes through several processes, different activities, lectures, assignments, personal reading, library, and all that. So the training set is fed to our selected model, algorithm, so that it can learn appropriate parameters and features used in prediction. That is, it can create or learn the relationship that exists between our input features and our target class, or among the features in the case of unsupervised learning. We'll get to that level or that stage. I'll explain that. Training requires patience and experimentation. It's an iterative process actually. So once training is complete, the model can be refined using the validation set. Remember I told you, I said the training set and the validation set are used to train the model iteratively until we get a desired model performance. Then we move to the final testing phase. This may involve modifying, or discarding variables. Remember, under feature engineering, I said again that sometimes when the model is tested, we can go back and re-engineer the features to obtain better model results or better result in this instance. So as you can see, here we say this may involve modifying or discarding variables and includes a process of tweaking specific settings. Here we call it parameters. until acceptable or unacceptable accuracy level is reached. The tuning of the parameters is referred to as hyperparameter optimization. Remember, the student, as I said earlier, has some parameters, the ability to learn, what the level of learning, for instance, what the student has learned, the level of learning, the time it took to learn, the ability to learn. All of these are, parameters that are specific to the student. So in order to improve the performance of the student can actually try to, tune these parameters. What have I learned? How well have I learned it? How long have I learned it? What is the retention capability? What is my ability to write it? Write what I have learned, to summarize them. So all of these factors I talked about, they're actually parameters that are specific to the student. The same thing applies to a model. A model also has different parameters. Remember that under model framework, machine learning framework, we said y equals f of x, comma, w. Our f in that instance is the prediction function, that is the trained model. And our w is the set of parameters that are available for that trained model, that model has actually used to, learn during training. So we can tune. Hyperparameter optimization means tuning the parameters to improve the performance. When we say improve the performance, is that to improve accuracy or to reduce error made by the model? The next stage is model evaluation. When we have obtained, the model has been trained, the next stage is to, evaluate the performance of the model. The model which is the second phase, actually. Remember, we have the training phase and the testing phase. The second phase, which is the testing phase, the model is exposed to a testing set. And the performance of the model is measured or assessed using some metrics. For instance, accuracy. How well does the model predict the class? Or how good is the prediction of the model? We also have, other measures. For instance, F1 score. For instance, precision. For instance, recall, sensitivity or specificity. These performance measures are also they also relate to the type of task being solved, either classification or regression. If we talk about classification task, we talk about model classification accuracy. We talk about F1 score, precision, recall, and others. Then, if we talk about AUC is also part of classification accuracy, classification measures. Sorry. Then we will talk about regression task. We talk about root mean squared error. We talk about mean squared error. We talk about percentage error. Different error metrics. Sorry. So here, our model is exposed to the test data to see how well they have actually performed, or how well they will perform in prediction. If the results are not satisfactory, then the prior steps, that is step probably step 2, step 1. Sometimes you can go as far as go back as far as step one, framing the problem. Maybe the problem has been framed in the wrong way, or maybe the data was not clean enough, or maybe the model was not trained efficiently, the training approach was wrong, the data sampling approach was wrong, the training approach, and maybe leave one out, was not the best, maybe consolidation is the best. It is sometimes good to go back and revisit the previous stages to see what has been done wrong. If the evaluation is not done properly, the model may not excel at fulfilling its desired purposes. So the next stage is communicating model's result. What we have explained, everything we have done, model development, model performance, model, all of these technical stages are not, known, or sometimes your stakeholders or the client may not really care about what you have done. It is, it is not advisable for you to spend a significant amount of time going through all the 7 stages, the first to 7th stage, and then being unable to explain, to interpret, and present the results to the stakeholders, to the way in which the stakeholders will understand what has been done in line with the framed problem. Your stakeholders or the clients are only interested in the result. So at this stage, communicating your result either to the audience, to your supervisor, to your to the clients or to the stakeholders is really important. And this can be done using visualizations, tables, figures, and the likes. The next stage is model deployment. This phase is actually required for industrial applications. When your model is complete, it is now ready for use. So for instance, let us talk about maybe Facebook. There is an inherent model that is working within the web-based application. For instance, if you watch a video on Facebook, you will realize that similar video are recommended for you. So there is a model, a recommender system, more like a model, that is working within the system that does that recommendation. So we say that model at that point has been deployed for production. It is now used for its intended particle applications. Application. So here, the model is not, gains independence from human. No interference with the model. The model works just based on what it has learned during training or during development, and now being used in the real application, just like the recommender, let's say the recommender model within the within Facebook web-based platform. So the challenge for the model remains whether it can outperform or at least match human judgment in different relevant scenarios. Our model is expected to perform on average, what a human being could do, either in terms of accuracy or in terms of, the activities solving that problem. The prediction step is what the end users see when they use the machine learning model within their respective industry. Again, I say again, for instance, the Facebook application, you do not see what is going on at the abstract level or within this system. All you see is that you watch a video and Similar videos are recommended for you. That is a very seamless experience, an interesting experience. Initially, before the advent of these technologies, when you watch a video, you have to search for something similar. Here, you don't have to do that. As you watch, it tends to generate similar videos. This is just a case of what we call association rule mining in machine learning under um, unsupervised learning. For instance, um, what we call clustering. We have clustering, we have association rule mining. So one of the tasks performed under association rule mining is what we call a market basket analysis. When we get to that class, we'll explain that in detail. So the model deployment is usually performed by a machine learning engineer who combines the skill of a data scientist and software development. And finally, we have monitoring models. Unfortunately, deploying a model is not the end of a pipeline. So model must always be monitored after deployment to ensure that they are working properly. This is necessary because the data the model was trained on may no longer be relevant for predictions after a period of time. I would say, for instance, let us look at cybersecurity, where criminals are always coming up with new ways to hack, systems. Also, sometimes time series data may not really may have probably been outdated and may not be relevant for the data. There's this there's this thing we call concept drift in machine learning, where the data that was used previously to train a model might have changed. The distribution of that data might have actually changed and may not be relevant in prediction. So such a model that was trained on that's sequential data or time series data or a concept drift based data may perform poorly in the future if such model is not updated with current data from similar distribution. So this brings us to the end of the first module, where we have discussed where we have been introduced to the concept of machine learning. We discuss machine learning, why we learn, the machine learning framework. Then we talk about the machine learning pipeline, starting from the first phase to the last phase, problem formulation to monitoring models. And by next week, due to time, we'll talk about generalization and learning methods in machine learning, where we talk about, for generalization, we're talking about how well does a model learn from data. Imagine a student that has really learned. The student has gone through several lectures, assignments, personal reading, and all that. The student again, if the student learns sufficiently, the student tends to perform well during the exam. That is the prediction. But if student does not learn the content of that course sufficiently, the student may perform poorly in the exam. So if the student learns too well, or we say if the student learns the content of that course and noise, that is things that are not relevant to the course, the student may tend to forget what he or she has really learned during the exam. So in that case, the student tends to perform poorly in the exam, then perform well, doing maybe group discussions and all that. So if the student has learned more noise, a lot of noise with the content of the course, student tends to perform poorly, a bit low in the exam. We say in that instance, we say the student has experienced an overfitting problem or overfitting. But if the student does not learn sufficiently the content of that course, maybe there are maybe 15 topics to be covered or 10 topics to be covered. The student was able to cover, let's say, 3 or 4. Such a student will perform poorly in the exam. So in that case, we say the student is has experienced underfitting. So a model that learns, that is trained on the data and also learns noise in that data, the model will experience problem of overfitting. In that case, we say the model is experiencing high variance and low bias. That is high testing error, low training error. But in the case of overfitting, model overfitting, where the model was not sufficiently trained due to maybe less training data or low complexity in the model, such a model will experience underfitting. And in that case, we say the model is experiencing, high testing, low testing error and low training error. So all of this will be discussed in our next class. For learning methods, we talk about the different learning categories that we have in machine learning. One of it is we say supervised learning. They are classified into supervised, unsupervised, and semi-supervised. And also we have reinforcement learning. So all of this will be discussed in our next lecture. So it's nice to see you. Please, if you have any question, reach out to me, via email or course link, and you can also book an office hours with me if you would like to, discuss this concept, what we have talked about. In there are areas that you do not really understand. I'm available to, provide assistance and also more context into the lecture. So thank you again and have a great evening. Take care.